Hi once again. We will be defining the term decibel in here. This term is widely used in electronics, especially the communication systems. Why do we need that? Let me explain it. Assume that you're going to throw a function and let's assume that's frequency. So in electronics, the frequency range that we use is very wide, isn't it? So it could be 10 hertz, and it could be, let's say, 1 million hertz. That's megahertz, isn't it? There is gigahertz as well. Mega is 10 to the power 6, giga 10 to the power 9. So 10 to the power 3 is kilo. It goes like that. So the range is quite wide here. So if you would like to draw a function which is the function of frequency and show it here, not easy to show that 10 hertz and gigahertz on here. So what we do, we write log f here. When it is log f, that is 1, that is 2, that's 3, that's 4. So this 1 is 10 to the power 0, so that's 100. That is 1000, and that is 10,000. Goes like that. So why it is 4? Because 10 to the power 4 log 4 is equal to 4, isn't it? So that's 4. But I am representing, by this 4, I am representing 10 kilohertz. So if you write the log f here, so you can represent all these frequencies on this line going to the high values. So if you want the similar things on this axis, how are you going to do it? So to do this, we use this term decibel. So this here, that circuit here, represent a communication system. A communication system has a load here, and if the input resistance seen from the left hand side here is equal RL, it is a good communication system. So within a communication system, what is important is this: the signal power that you have at the input and signal power that you have at the output is critical. Why is that? Because if these are equal, that means there is no power loss within the circuits. So it is directly related to the efficiency of your circuit. That's why it is critical. So decibel is defined, decibel here is defined on the output power over the input power. So the power here, that means useful power, and the power, your signal power before you apply the signal to your circuit. So logarithmic operation comes, as I explained here, logarithmic operation here, 10-based logarithmic operation multiplied with 10. So if it is the ideal communication system, then Rin, this resistor seen from the left hand side, is going to be equal to the RL load resistance. So if I transfer these voltages, these powers to the voltages, so it's going to be the power of a resistor is voltage multiplied with current. So if you write the current in terms of voltage is V over R, definition relation, so V square over R, that's the power. So this is what is written here. and that is the power of the load. If Rin is equal to RL, so the R's disappears, and what is left is R out Rn square. So if you get the logarithm of it, you're going to end up with this, isn't it? So this is the output over input is transfer function, isn't it? So the model of Hj omega model, you can consider that as a gain or the model of the transfer function. Then this is the commonly used decibel in terms of voltages, decibel definition in terms of voltages here. So this term, although it seems as if there is a dimension in here, there's a unit, it seems as a unit, but it is not a unit. Why is that? Because voltage over voltage is unitless, isn't it? So there is no dimension there. So you might call this that decibel represent the level. How it represent the level, it is shown here. When it is 10 to the, when this is 10 to the point 0, so that means your ratio is equal to 1, isn't it? If you get logarithm of it, it's going to be 0. So that means if the ratio is 1, your decibel value is 0. If your ratio is, let's say this is 1.5, when it is 1.5, output is 1.5 times bigger than the input, so this is, as a level, is 3. If it is doubled, so it is 6. If the increase is doubled, is multiplied by 10, so your level is 20. So if you make it 1000, for example, it becomes 60. So if you move from here to here, you've got to multiply this by 10, but this is not multiplied by 10, but multiplied by 2. So you could see, you could show the higher value ratios on this axis. That is the benefit of using decibel. So let's come to our filter characteristic case. This axis is going to be 8j omega module. Now we are saying, in order to show these high values on this axis, we are going to write here decibel, and this is going to be 20 times log 10. This is it. So what this decibel is all about. So in here, ratio is positive, in here it is negative. Why is that? If it is less than 1, that ratio is less than 1, that is attenuation, then it becomes, the level becomes -0, -3, -6, -20, -40, -60. You got to remember 1000 is 60 decibel level. 1000 represents 60 decibel level. As I said, this is a unitless term. That's the end of this video.